In this video, we want to do a few examples of some different applications of the derivative. In this example, it says, at what points on the graph of f is the tangent line horizontal? So that's the first part of this problem. We want to find where the tangent line is horizontal. Well, if the tangent line is horizontal, that means that the tangent line has a slope of 0. Another way to say that is, where is the derivative function equal to 0? If we want to find where the derivative function is equal to 0, we need to first find the derivative. We can find the derivative by differentiating term by term. So f prime of x will be equal to 2 times the derivative with respect to x of e to the x minus the derivative with respect to x of 6x. The derivative of e to the x is e to the x. So the first term in the derivative function is 2e to the x. And then the derivative of 6x is 6. So the derivative of f of x is 2e to the x minus 6. This is the slope function. This function will give us the slope of the original function at any value for x. And we want to know where the slope is equal to 0. So we want to know where 2e to the x minus 6 is equal to 0, because that's where we'll have horizontal tangent lines. So let's solve the equation 2e to the x minus 6 equals 0. Adding 6 to both sides gives us 2e to the x equals 6, and then dividing both sides by 2 gives us e to the x equals 3. Now let's solve this exponential equation by taking the natural log of both sides. Using one of the laws of logarithms, we can now move the x out of the exponent's position and down into the body of our equation as a coefficient. And the ln of e is equal to 1. So we have x equals ln of 3. The natural log of 3 is really close to 1.1. So when x is about 1.1, we could expect to have a horizontal tangent line on the graph of f of x. Now let's find at what points the slope of the tangent line is equal to 12. So it's the same process. We now just take the slope function and set it equal to 12 and solve. Solving this equation in the same manner gives us x is equal to the natural log of 9. In this example, we're asked to find an equation of the line tangent to the given curve at a, or when x is equal to a. And our curve is y equals e to the x. And our given x value is natural log of 3. So we want to find an equation of a line tangent to y equals e to the x when x equals natural log of 3. To come up with that equation, we're going to need the slope of the tangent line when x equals natural log of 3. So let's find the derivative. The derivative of function y with respect to x is e to the x. Now let's evaluate this slope function when x is natural log of 3 to get the slope of the tangent line at that x value. That gives us e raised to the natural log of 3, which is just 3. So this is the slope of the tangent line when x equals natural log of 3. Now let's use that information to find the equation of the tangent line. We'll use the point-slope form of a line to do that. To use this, however, we have to have a point on the line, and we have to have the slope of the tangent line. Well, we have the slope of the tangent line, that's 3. And we have an x-coordinate on the line, which is ln of 3. But we need a y-coordinate to go with that. We get the y-coordinate by substituting the x-coordinate into the original function. When we substitute ln of 3 into the original function e to the x, we get e raised to the ln of 3, which we just proved over here on the left is 3. So the y-coordinate is 3. So that gives us y minus 3 equals 3 times the difference x minus ln of 3. When we distribute on the right, we get y minus 3 equals 3x minus 3 ln of 3. Now add 3 to both sides to isolate y. So the equation of the line tangent to the graph y equals e to the x when x equals ln of 3 is y equals 3x minus 3 ln of 3 plus 3. Let's take a look at this example. The distance an object falls when released from rest under the influence of Earth's gravity and with no air resistance is given by the function d of t equals 16t squared, where d, the distance, is measured in feet and t, the time, is measured in seconds. A rock climber sits on a ledge on a vertical wall and carefully observes the time it takes for a small stone to fall from the ledge to the ground. The first thing we need to do is compute the derivative of the function d. Using the power rule, we differentiate d of t as 32t. Now, if it takes 6 seconds for the stone to fall to the ground, how high is the ledge? In this part of the question, we are given a time and we need to find a distance because the height of the ledge will be equal to the distance that the stone fell. We can use the original function to make this determination. We know that time is 6 seconds, so we substitute 6 into the original function. And a simple calculation tells us that the stone fell 576 feet in 6 seconds. That's also the height of the ledge. And this question is a follow-up from the previous question. We want to know how fast is the stone moving when it strikes the ground in miles per hour. In other words, we want to know the stone's instantaneous velocity when it strikes the ground. Well, in the previous problem, we knew that it took 6 seconds for it to strike the ground. And we found in the previous example that substituting 6 in for the time in our original function told us how far the stone had fallen. But now we want to know the velocity of the stone after 6 seconds. To find the velocity, we have to use the derivative function. Evaluating the derivative function at 6 seconds gives us 192 feet per second. Now that's our answer. That's our instantaneous velocity in feet per second, but we need it in miles per hour, so we have to do a couple of conversions. 192 feet per second is 691,200 feet per hour. We get that number by multiplying 192 by 3,600 because there's 3,600 seconds in 1 hour. And to change that from feet per hour to miles per hour, we divide the 691,200 by 5,280 because there are 5,280 feet in 1 mile. That gives us about 130.9 miles per hour.